Today's lecture will be the continuation of previous day's lecture. In previous day, we have gone through a design example for designing of lacing system. So, in last lecture, we have discussed how to design a lacing system, how to provide the length of the lacing, width of the lacing, thickness of the lacing, then what will be the spacing between two lacings, what will be the angle of inclination. So, all the details of lacing has been discussed. Today, we will be going to discuss on the connection part. Connection part means the connection between lacing and the column, main column. So, as lacing is taking certain amount of load, so we need to design the lacing with the column in such a way that the connection between these two can withstand the developed load. Developed load, how to calculate, we have discussed. Today also we will calculate the developed load, that means the transverse shear what is coming 2.5% of the load which one means of the compressive load which is acting on the main member, main compression member. So, from that we have to find out the value of the shear, and then we can find out what will be the connection details. Connection details again we will discuss today two type of connections. One is bolt connection, another is weld connections. So, for bolt connection, how we will be designing the bolt and how we will be designing the weld, those things will be discussed today. So, before going to do that, first I will very quickly go through the previous day's example, so that we can rewind our earlier calculations which will be required for calculating the design strength of bolt and number of bolt or weld length. So, very quickly we will go through the earlier lecture whatever we have given part of that. So, example was this, that is so example is this which is written here, that design a laced column of 10.5 meter long to carry a factor load of 100 kilonewton. The same example, and here we will be using two channel section placed back to back, and we will try to find out the design of the lacing system with bolted connections and design of the lacing system with weld connection. And weld connection we will consider this case as side weld. We can consider shop weld also, in that case that gamma MW value will be changed. So, according to the weld means type of weld, whether it is side weld or shop weld, the gamma MW has to be taken. So, if we remind the earlier lecture, we can see that we got already the solution of this, that is ISMC 300 back to back we have provided with a spacing of 184 millimeter, right. And also we found the L0 by RYY we calculated, where L0 by RYY is coming this, where L0 value has been calculated in earlier slide, and this is becoming less than the 0.7 times L by R or 50. Therefore, the L0 value whatever we have considered 568, L0 value means if we see the lacing like this, then this is the L0 value, right. So, lacing is going like this. So, L0 value we have considered from this. Now, the maximum shear also we have calculated, which is 2.5% of the compressive load, and the transverse shear in each panel has been considered as there are two parallel face. So, the value of n we have considered 2. Therefore, transverse force and transverse shear in each panel is coming this much, and compressive force in lacing will be transverse shear into cosec 45 degree. Why cosec 45 degree? That transverse shear is coming in this way and compressive force will be in this way. So, while making the equilibrium equation, we can find out this value. So, the compressive force in lacing bar we obtained this value will be required in today's calculation, that is 17.67 kilonewton. This value is the compressive force in the lacing bar, and while designing the connections we have to design against this load. So, we have to remember this load which are coming here. Then what we have calculated is the thickness of the lacing plate, and using so the thickness of the lacing plate will be calculating. Before that we have to calculate the length of lacing plate, and lacing plate we got like this, because the minimum width of the lacing for lacing plate we will be calculating, because the spacing between these two was this, and gauge distance was 50. So, according to that the length of lacing plate, which is this, has been calculated, right. Another thing is the minimum width of lacing plate is 3 into d, that has been calculated 48, and so we have provided 50 mm with lacing plate and 402 mm length, and thickness we will be calculating as per clause 7.6.3. We can calculate the minimum thickness of lacing plate as 1 by 40 into length of flat, and we know that for double lacing it will be 1 by 60. So, lacing thickness we are finding like this. So, we can use 12 mm thick plate and width as 50 mm. And now, we have to check the slenderness ratio. For checking the slenderness ratio, we will be finding the minimum radius of gyration, which is for lacing plate it will be T by root 12, and that we can find out like this. Remember that minimum radius of gyration, if we consider angle section, then we can find out the minimum radiation gyration from the IS code, means SP6. From SP6 the minimum radius of gyration or VB of the angle section we can find out, and from that we have to calculate, right. And as we are using lacing flat, we directly found this value. So, radius of gyration we are getting 116, and which has to be less than 145, that means the lacing length is fine, right. So, next what we will go, we will do the we will find out the FCD value. FCD value means compressive stress of the lacing member. So, for L by R is equal to 116, which we have found, and we are using FY 250 grade of steel, and for flat plate the buckling class will be C. So, according to that condition we can find out the value of compressive stress from table 9C, which will be this 88.06, and this can be found from interpolating results for L by R is equal to 110 and L by R is equal to 120. So, this is how we can find out the FCD value, right. And the design compressive force also we can find out, and this design compressive force has to be greater than the force acting on the lacing member. The compressive force acting on the lacing member, which we have calculated as 17.67 kilonewton. So, this is the design compressive strength, which is more than the external compressive force on the lacing member. So, that means the design is okay, right. In every case I have told that if the criteria is not satisfying, then we have to increase either the thickness of the plate or the width of the plate, means case to case we have to check. Sometimes we may have to reduce the length of the lacing plate by changing the angle of inclination. So, in this way we have to find out which one, means which dimensions and which orientation the design will be, means lacing will be provided, so that the design of the lacing will be safe. Now, the tensile strength of the flat we have to find out, because we will see the tensile strength or compressive strength, both the cases this value will be same 17.67. because in lacing member the whatever axial force is coming, that may be tension or compression. So, for both the case, means for compression and for tension, we have to check whether the design strength due to tension or compression is more than this 17.6967 or not. So, according to the tensile strength, we can calculate the design tensile strength of the member due to yielding of due to rupture of the critical section. So, that we can find out, this will be TDN value. So, TDN value we can find out from this formula, that is 0.9 into B minus DH into T into Fu by gamma m1. So, after putting this value, we can find out the TDN value as 113.36 kilonewton, and similarly the TDG value, that is yielding due to gross strength due to gross yielding of the section, that is Ag Fy by gamma m0, and by putting the gross area as 50 into 12 which is B into D B into T and Fy, then we can find out the TDG value as 136.363 kilonewton. So, the tensile strength of the flat will become minimum of this 113 and 136, that means 113.3636 kilonewton, and this is greater than the tensile force coming in the lacing bar. So, this design is okay. If I have already mentioned that if design is not okay, then what we need to do, we have to change the dimension of the lacing, so that the design strength become more than this 17.67 kilonewton. Now, we will come to bolted connections. Now, first is we are going to consider the bolt connection when lacings are not overlapped each other. That means, when our case is like this, say suppose this is a column member, vertical column member, and lacing is provided in this way with a certain inclination, and this is not overlapped. That means, separately it has been joined like this, right. So, force we can find out what is the force are coming, right. Now, for finding out the force means we will provide the bolt here, and we know what is the force, axial force is coming into picture on this single lacing, right, that we have calculated earlier. Now, we have to find out first what will be the bolt strength which the bolt strength of the member, right. So, if we use 16 mm bolt, because in question it is given 16 mm bolt of grade 4.6, then what we can find out? We can find out the strength of bolt in single shear, because this is separately, it is not overlapped, separately it is joined. So, this will be basically a single shear. So, due to single shear, VSB we can find out, right. VSB will be ASB into Fu by root 3 by gamma MB MB, and here what we have considered, the shear plane is not going to pass through the threaded portion. So, in place of A and B we are considering ASB. So, if we consider that, we will be getting pi by 4 into 16 square into 400 is the strength of the bolt, yield strength, ultimate strength of the bolt, then this into 1 by gamma MB is 1.25, right. So, if I consider this, then I will get the value as 37.147 kilonewton. Now, as 16 mm diameter of bolt we are using, so I can assume the pitch as 2.5 D minimum pitch. So, it will be 40 mm minimum, and edge will be 1.5 D0, that means 1.5 into 16 plus 2, that is 18, it will be 27. So, we can provide say pitch as say 27 sorry 40 50 mm, we can increase little bit, and say E as say 31 mm, because or 30 mm, right. So, now Kb will be the smaller of this E by 3d0, P by 3d0 minus 0.25, Fu B by Fu and 1. So, if we consider this, we will get the value of Kb as 0.57, right. Now, considering value of Kb as 0.57, we can find out the bearing strength. Bearing strength VdPb. In fact, this I can make this not VSB, actually VDSB, because you have divided by gamma MB, VDSB, design shear strength, right. So, bearing strength VdPb will be 2.5 Kb dTFu by gamma MB, right. So, if I provide this value, I can find out, that is 2.5 into Kb is 0.57 into 16 into 12 into Fu is 410 by 1.25. So, this is becoming 89.74 kilonewton, right. So, strength of the bolt I can find out as 37, means lesser of these two, 37.147 and 89.74. So, lesser of those two, the strength of bolt will become 37.147 kilonewton, right, kilonewton. So, the number of bolts required will be the force by bolt value, say R or BV bolt value. So, force is 17.67 kilonewton, which we have calculated earlier, and the bolt value is 37.147. So, this is becoming 0.5. That means, at least one bolt has to be provided at each end, right. So, one bolt we are going to provide. So, this is one case, and another case will be that if the bolts are means if the lacings are overlapped each other. This case, if lacings are overlapped each other. So, if lacings are overlapped each other, means this will be means connections will be like this. Say for example, this is the main member and we have a lacing here and another lacing is so like this, right. Right. So, bolting will be done here, and that means the lacing in this orientation we are making lacings are overlapped each other. So, in this case the design shear strength of the bolt VDSB will become twice the shear strength of the due to single shear, because this is acting as a double shear. So, whatever shear strength we got earlier, that will be double of that, right, double of 37 kilonewton. So, 37.147 kilonewton, right. So, this is becoming 74.294 kilonewton, because in this case it will be in under double shear, right. Now, strength in bearing will be same, we can find out the strength in bearing VPB, VDPB, that will be same 2.5, Kb was 0.57, D is 16, T is 12, then Fu is 410 by 1.25 gamma MB. This is coming same as earlier 89.74 kilonewton. So, what we could see that the strength of bolt in double shear is coming 74.294 and strength of bolt in bearing is 89. Therefore, the bolt value we can consider as 74.294 kilonewton, right. Now, number of bolts required. So, here we can see that what will be the force, resultant force acting on the bolt, that will be, we can find out the resulting force will be V by N, right, into cot 45 degree. How we are getting this? Because you see, if we resolve this is theta, right. So, if this is theta, then we can find out 2 f cos theta is equal to 2 into 2 f cos theta. So, 2 into f means V by N, earlier we got cosec theta, right. So, the resultant force R will become in this bolt will be f cos theta plus f cos theta, right. So, both will acting in together vertically, f cos theta and f cos theta. So, 2 f cos theta, again f is equal to V by N cosec theta. So, 2 into V by N cosec theta into cos theta. So, this will become 2 into V by N cot theta, right, 2 into V by N cot theta. So, we can find out the resultant force as R is equal to 2 into V by N cot 45 degree. Therefore, this value will become 2 into 12.5 into cot 45 degree, that means 25, cot 45 degree is 1. So, 25 kilonewton, right. So, resultant force is coming 25 kilonewton and the bolt value is coming 74.294 kilonewton. Remember, this is different from the earlier one. In case of earlier orientation, our bolt value was different because of the single shear and the resultant force was also different, because here resultant force will be the means cost component of these two force, right. So, number of bolt I can find out, that will be resultant force as 25 and bolt value was 37. So, that is becoming 0.7, that means here in this case also it is coming 1. That means, if we provide one bolt at each end, then that is sufficient, right. So, this is what the bolt connections are made in this way. Now, after bolt connection, another thing we need to remember that is important, that when we are connecting the compression member, the built up member by lacing system, we have to provide tie plate at the end, say for example, this one. So, this will go on like this, right, and finally, we have to provide the tie plate at the end. At top and bottom or at the end of both, means at both end we have to provide tie plate. So, we need to, this is called tie plate, right. So, we need to find out the dimensions of the tie plate, and this is given, the details are given in clause 7.7.2.2, right. In clause 7.7.2.2 it is given. So, now the as per this codal provision, the mean effective depth D can be found as S plus 2 CYY, where if we consider such type of channel sections back to back for this case, then this is CYY, somewhere here CYY, and this is S. So, the effective depth will be this one, and it should be greater than 2 into B, where B is the flange width, means whatever width we are getting, this flange width is called B. So, here we are getting S as 184 plus 2 into CYY we found earlier 23.6, which are becoming 231.2, and it should be greater than 2 into B. B was the flange width, which was 90. So, this is 180. That means, the effective depth is greater than 180. So, it is okay, right. Now, minimum edge distance also we need to provide. Minimum edge distance means, when we are providing the bolt connections here, say for example, here, now we have to provide certain edge distance, right. Means if I enlarge this here, it will be something like this. So, suppose these are the bolt connections and this is D, right. So, overall depth is basically D plus twice E, because minimum edge distance means edge distance is, if it is this, then we have to include the edge distance. So, depth, the total depth will be D plus 2 into E. Okay. Now, E we can find out, E will be 1.5 D0, D0 means 18. So, 27. So, we consider say 30, right. So, the overall depth I can find out from this, that is earlier we found effective depth as 231.2 plus 2 into E is 30. So, this is becoming 291.2. That means, the minimum overall thickness of the plate, overall depth of the tie plate will be 291.2, or we can provide little higher side, that is say 300 millimeter, right. So, we are providing 300 millimeter tie plate, and the length I can find out, length will be simply S plus 2B, right. Length will be S plus 2B. So, 184 plus 2 into 90. So, length of tie plate will be 364. If we see in the picture, if this is the cross sectional orientation, then this will be the tie plate length, right. This is B and this is S, right. So, 364 millimeter. Now, thickness of the tie plate we have to find out. Thickness is, as per Codal profession, this is 1/50th of the distance between inner bolts. So, in this case it will be 184 plus 2 into 50. Inner bolts means, if this is the G, then we can consider this is a G, right, and this is S and this is G, the gauge distance. So, basically we have considered 1/50th of A plus 2G, S plus 2G, right. So, from calculations I can find out thickness is 5.68 millimeter. So, we can provide 6 mm thickness. That means, we can provide a tie plate, of size 364. This is fixed because of the distance between two compression member. Then 300 is the depth and thickness is 6. So, this size of tie plate has to be provided, and we can provide certain diameter of bolt, say 16 diameter of bolt we can provide, and a sample figure has been shown here. I am going to show. This is the figure. Say for second case, if we see we are providing the tie plate of 300 mm depth and 364 mm length, right, and thickness as 6 mm, and this is the size of the lacing plate, and here it is overlapped. We in this case we are considering the overlapping of both the lacing members at a certain point. So, this is how we can make, and spacing between two lacing is 568 millimeter. So, this is how we can do the bolt connection. Now, coming to the weld connection, let us see how we can make details of the weld connection. So, in case of weld connection, if we see that here certain things are given which we need to know, that is the flange thickness is 13.6 mm, flange thickness of ISMC 300. Now, if flange thickness is 13.6, then the minimum size of weld we can find out from table 21 of IS 800. So, minimum size of the weld we can find out as 5 mm. So, strength of weld per unit length I can find out 0.7 into S, S is the size of the weld. So, 0.7 S into Fu by root 3 gamma mw. For side weld, gamma mw value is 1.5 as we know from table 5, right. So, these values are coming as 552.33 Newton per millimeter. So, strength of weld per unit length we can calculate from this, and required length also we can find out, because the total force means axial force acting on the member is 17,670 Newton, 17.67 kilonewton. So, the required length I can find out from this, force divided by strength of weld per unit length, right. So, 32 millimeter length is required. Now, we need to add some extra length because of the at the edge, at the end return. So, 32 plus 2 into 2 s, size of the weld is s. So, 2 s at each end it will be required extra. So, 2 into 2 s will be total. So, 52 millimeter weld length will be required, right, and we can provide say little higher, say maybe 100 mm weld length at both ends. So, this is how we can calculate the weld length. Now, for this also we can calculate the tie plate dimension. So, for this the tie plate dimensions will be like this 184 plus this 2 into CYY. So, we can provide depth as overall depth 231.2 millimeter, which is can be increased to 240 millimeter. Here you remember, here there is no effective depth, right. So, in case of bolt connections we have effective depth, right. This is the overall depth and this is effective depth, but here in case of weld connections we are welding at the end. So, effective depth and overall depth will be same, right. So, overall depth we have calculated this, and we are getting means little higher side, means higher value, that is 240 millimeter. Remember, in case of bolt connection it was 300, we provided 300 millimeter. Now, here length of the tie plate will be as usual, means as we have considered in earlier case. So, length of tie plate will be 284. Then the thickness of tie plate we can find out, thickness of tie plate will be 1 by 50 into this, that is 5.68. So, we can provide a say 6 mm tie plate, or maybe say little higher, say 8 mm tie plate also we can provide, and the size of weld we can provide 5 mm, right. So, the final dimensions will be the provided tie plate of size 283 by 240 by 8 millimeter size, and connect it with 5 mm welds as shown in the figure. So, final dimensions is this 283 by 240 by 8, right. Now, why we have provided 8 mm where 6 mm is sufficient, because if we provide 6 mm then the size of the weld has to be reduced, again we have to recalculate everything. Therefore, we have provided little higher size just to match the results. So, the drawing will be like this, that is this is how the connections have been made at each end, and at the for the tie plate the connections have been made like this, right. So, when we will doing weld connections we have to do by this. Now, it depends what is the total length, and accordingly we have to distribute. It is not that total length will be will be entire length, right. We have to find out what is the total length L W, and we have to distribute in 3 sides properly. We may distribute like this also. Suppose this is the tie plate, we may distribute here, certain distribution here we can do, certain distribution here also we can do as per the requirement. So, in today's lecture we have demonstrated a connection between lacing member and the compression member. Connections two type, one is weld connection, another is bolt connection. Again, for bolt connections we have shown that if the lacings are overlapped and if lacings are not overlapped, how to calculate the forces for overlapping lacing and for not overlapping lacing, and then how to provide the number of bolt, because the strength of the bolt will be different for two cases. And in also we have found the dimension of the tie plate. How to find the dimensions of tie plate, that also has been demonstrated through the example in this lecture. And then again we have calculated the same for weld connections. Calculated means the length of weld, what will be the length of weld required, we have calculated, and how to distribute also we have shown, and how to calculate the length of weld based on the size of the weld, that also has been demonstrated, right. So, I hope this will be this example will make you clear about the connections between compression member and lacing member. Thank you.